Okay, sir. Now we are on live.
బాగా స్టార్ట్ చేయండి.
Good morning, one and all. So welcome to the third day session of FDP-2 on drug discovery and development. Before beginning the session, so here is a small video on our campus and how we are taking some precautions on COVID-19, so prevention of this coronavirus. Good morning, all. Welcome to the third day FDP-2 on drug discovery and development. So, before beginning the session, I would like to introduce our director, sir. So, Director Dr. Kumar V.S. Nemmani, Vishnu College of Pharmacy. So, holds a B.Pharm and M.Pharm pharmacology degree from Andhra University, Visakhapatnam. He has completed his PhD from Naipur, Mohali. Subsequently, completed his postdoctoral fellowship from McGill University, Montreal, Canada. So, he has 14 years of industry research expertise on drug discovery and development and managerial experience. So here I introduce our principal, sir, Dr. K. Prasad, completed his B.Pharm, M.Pharm from Andhra University, PhD from Andhra University, worked in various teaching designations, and professor in HKE College, Karnataka, serving as principal of a college from 2011, has wide research experience. Now I request Dr. Kumar V.S. Nemmani, Director, sir, to give a welcome note.
Hello everyone, welcome to Day-3 International Webinar on drug discovery and development. I'm thrilled with the overwhelming response in terms of the registrations. The number of registrations are crossed 1,000. I, on behalf of SLCP management, Sri K. Vishnu Raj Garu, Chairman, and Sri Raichandran Rathgopal, Vice Chairman, Dr. K. Prasad Garu, Principal, and staff of SLCP. welcome and thank you all for being part of this webinar series. I also thank the speakers of this webinar series, Dr. Srinivas Reddy, who has just joined now, and the earlier speaker, Dr. Prashant, for making this event a grand success. And this note, I also thank all the principals and the senior staff of other colleges who are continuously supporting this event. And I also must thank Anil Kumar, organizing secretary, and Dr. Sujit Kumar, the program coordinator, for nicely coordinating the each and every event. I must thank Dr. Jagdish Panda, who has just joined now in this webinar, who is a chemist and the principal of Dr. College of Pharmacy, who has been a constant support and motivation for me in organizing this kind of a webinar series. I am very delighted and happy that Dr. T. Jagdishwar Reddy, my family friend, has accepted for being part of this webinar series. So I have a lot to say about Dr. T. Jagdishwar Reddy. I must add about him is that he has his degrees from the top institute from India, I would say Indian Institute of Science, and his postdoc from University of Chicago, University of Illinois, that is Chicago, and at another wonderful institute. And he worked with the top MNCs in the world, like the Merck, Vertex, Shire, and many other companies. I think he has an extensive experience in medicinal chemistry, and you all see the taste of medicinal chemistry and their role in drug discovery today. So this talk will make it more intense toward the science, because general aspects have been nicely covered by the earlier speakers. So it's so we focus towards the chemistry. It's more celebration for the chemist today. And when I look at Dr. Jagdish, I will remember the two incidents in my life which I cannot forget. One is the trip to the Niagara Falls, and the other one is the trip to the Thousand Islands. And in every trip, we also discuss science. And I have many encounters with Dr. Jagdish Reddy and the discovery development. At every interaction, I learned a lot from Dr. Jagdish Reddy. So at this note, I must thank and welcome Dr. Jagdish for this webinar series. And this note, I also like to welcome all the participants who have joined just now, and also thank for their active participations in the past webinar series as well as the current webinar series. I'm glad to announce today that we are going to send the flyer for the upcoming webinar series, again an international webinar series being organized by the Pharmacy Practice Department as a role of pharmacist in healthcare, so which is coming up from the next week onwards. So I request and suggest to every one of the participants to participate again in that event. So at this note, I thank Dr. Jagdish Reddy and all the ex-speakers who have done a wonderful job in making this event successful. So I believe that today is as well will be a very enriching experience for all of us in the field of the chemistry and their role in drug discovery and development. So thank you all. Have a good day.
So next, introducing our today's speaker, Dr. T. Jagdishwar Reddy, Research Officer at Institute of Research in Immunology and Cancer, Montreal, Canada. So his education postdoc organic chemistry at University of Chicago, 2000. His experience, so he worked as a research scientist in Zamboni Chemical Solutions, senior scientist in Vertex Pharmaceuticals, research scientist in Virochem Pharma, senior research scientist in Merck, and he has several publications to his credit in high impact journals and journal groups like Elsevier and ACS, and worked on several core areas like methyl radical EPR imaging, discovery of thiophene 2 carboxylic acids and potent inhibitors of HCV polymerase, inhibitors of cathepsin C, and so on. So we are very happy to have your lecture, sir, and seeing your core areas of research. We are really fortunate to hear to you. Over to you, sir.
Andariki namaskaram andi. I want to say a few words about Kumar. Thank you very much, Dr. Kumar Nemani, Director of the Institute, and Sujit Kumar, Program Coordinator, Mr. Anil Kumar, Organizing Secretary, and Chairman Raju Garu, and Vice Chairman Ravichandra Rajagopal Garu, and the Vishnu College of Pharmacy, for giving me an opportunity to talk about some of the work that I have done it. So before I begin, I would like to say a few words about Kumar. So we had a 2 years of overlap during his postdoc time. So we are living next to each other. He's a very nice guy, and he has a high caliber of science, and he won't accept the defeat so easily. So it's good that he's taking care of the college. So I'm very confident that he will bring up the Vishnu College of Pharmacy into the next level. So he asked me to give a talk on the drug discovery, or what is the role of chemistry in the drug discovery. So we had 2 great talks last 2 days. Dr. D.S. Reddy has given a comprehensive overview on the drug discovery and what is the role of chemistry during lead optimization. And the next talk was given by Professor Prashant Kotkar. And it's really, I agree that TB is very bad. I think we really need medicines, effective medicine to treat or eliminate the tuberculosis. As he mentioned that, if there is no benefit, so those developing countries are not going to work on the TB because there's no market for that, because all the TB is prevalent in developing countries, underdeveloped countries. So today I'm going to talk about hepatitis C. So hepatitis is a major problem worldwide. So I have chosen the topic, which is discovery of hepatitis C NS5A replication complex inhibitor. Because after discovery of this class of compounds has changed the landscape of the hepatitis C, the way they treat. So as you can see during my presentation, has some problem. Okay. So here is outline of my presentation. I'll give a brief overview on hepatitis in general. Before I go into NS5A replication complex inhibitor, I will give you a brief update on the discovery of NS5B RNA polymerase inhibitors. And the second class is discovery of NS3A protease inhibitors. And then later I will present you case history of the discovery of NS5A inhibitor by BMS. And then followed by the identification of NS5A inhibitors by others. So it's a fast follow-up. So I end up with the final summary of FDA approved drugs. Virus is a submicroscopic infectious agent that replicates only inside the living cells of an organism. There are more than millions of viruses that can infect living organisms, which includes plants and bacteria, etc. So its basic structure of the virus is it has a genetic material, either DNA or RNA, which is coated with a protein. It's called a capsid, and it is wrapped with the outside membrane, which has a lipid envelopes such as glycoprotein. So these viruses, either DNA, RNA, they were classified in 7 classes by Dr. David Baltimore. I'm not going into detail on all those things. So the main difference with the DNA and RNA virus is DNA virus replicates in the nucleus, RNA virus replicates in the cytoplasm. We have seen a number of outbreaks for the past 100 years. One of them is influenza A, is a Spanish flu in 1918, which is born through air. And then HIV pandemic, hepatitis C, another one, Epstein-Barr virus, which is caused by the contamination of the saliva, norovirus, which is transmitted through food or water, dengue, we have seen swine flu, Ebola, mumps recently, and then the most recent one is corona. Corona has different, there are three main viruses that cause infection. SARS, SARS is nothing but severe severely acute respiratory syndrome. MER is like a Middle East respiratory syndrome. This is a COVID-19. So, because every day humans, we face constant face against viruses because we develop the immunity, so it's clear the viruses. So this is the overview of hepatitis. I'm going to talk about what HEPA means, a liver. Hepatitis means a disease. So this is the disease of the liver. So hepatitis is the inflammation of the liver. Okay, there are mainly 5 types of hepatitis virus, which is A to E. So the hepatitis A and hepatitis E transmitted through the contaminated food or water, mostly prevalent in developing countries and developed countries due to poor sanitation. Hepatitis B, C, D were transmitted through contaminated blood or body fluids. So B and C contaminated through the blood transfusion, sexual, and also it can transmit through mother to baby. Okay, so this hepatitis C virus, when there is an acute infection, you may or may not develop symptoms. Okay, so jaundice is called a yellow fever, and you can have a dark urine, nausea, fatigue, and sometimes vomiting, and abdominal pain. Okay, so what is most important to take away is hepatitis C is asymptomatic, means there are no symptoms for the period of 15 to 20 years. So this is very important. 80% of the people do not show at all. Okay, so, and there is a vaccine for hepatitis C. Usually, infected within few weeks, or immune system will clear, and also if there is any further infection, it can also prevent the hepatitis C. So whereas hepatitis B, there is a vaccine available, and also there are direct antiviral agents. So it's most important is hepatitis B is very difficult to cure. It's only direct antiviral agent does not cure hepatitis B. The only thing that what they do is they bring down the virus level low so that the immune system will take over and clear the virus. So that's a distinct feature. So hepatitis C, so 30% of infected cases, so our immune system will clear the virus within 6 months. If it is not, and it go into chronic stage, so there are no vaccine for this virus, but this is the one today I'm going to talk about. There are efficient direct acting antiviral agents that are available. So in case of hepatitis D, hepatitis B vaccines provide protection from HDV infection. Hepatitis E, so basically vaccine is available in limited countries. It's available in China, not widely used elsewhere. So hepatitis B and C are the major causes of liver cirrhosis and liver cancer. Okay, so when it goes into chronic stage, that's where slowly, it's like a slow poison to the liver. So what are the global distribution of hepatitis C? as you can see, the size of the pie chart is proportional to the number of infection. So there are 6 genotypes worldwide. Okay, there are under 60 million people who are infected. Genotype 1, today, that's the one I'm going to talk about during my optimization. Genotype 1, genotype 3, which contributes a majority of the worldwide infection, which is about 76%. And genotype 2, 4, 6 to 23%, genotype 5 is less than 1%. So it's very important, the only developed countries, unless there is a disease in the developed countries, the pharmaceutical companies are not going to work because this is a profitable business. So in US and Europe, so genotype 1, so remember genotype 1 is the major genotype, which affect more than 70% people. South Asia, which includes India, Pakistan, Nepal, and Afghanistan. So genotype 3. So in India, genotype 3 is the major infection. So among those infected with hepatitis C, 1 to 5% develops liver cirrhosis. As you can see in the picture here, there is a fibrosis here, and then fibrosis slowly convert to cirrhosis and carcinoma. Okay, when you are in that stage, you are too late, so that you have to undergo liver transplantation or leading to a death. Okay, so there are 10,000 people deaths per year in the US alone. So this figure is going to go down after discovering the hepatitis C drugs. So WHO estimated in 2006 that there are 400,000 people died from hepatitis C. So remember, there are a lot of people who are co-infected with the hepatitis C, like HIV and hepatitis B. So you have to diagnose, you can diagnose HCV by looking at antibodies test. If antibodies test is positive, which means that, let's say in the past you were infected, maybe you develop antibodies. So to confirm further, you require a nucleic acid test, such as finding the RNA level or HCRNA level. So who is at risk with this virus? Okay, people who born between 1945 and 1965, and also people who undergone blood transfusion, transfusion recipient before 1992, because after that they have implemented, we're not talking about in the US, after that they implemented a screening test. And also those people who undergone hemodialysis, and also children who born to infected mother, and also injection or intranasal drug abusers. Okay, so this is very important. And of course, prevention, there's no vaccine. So you just have to be careful about those things that I listed here. So what is available? Okay, in 2000, so PEG interferon 2A or 2B in combination with the ribavirin, okay, approved for hepatitis C patients. The treatment is very, very long, okay. It's 48 weeks, almost a year, okay. The sustained, here I talk about sustained virological response. This is called SVR. So that means that, so you should not have any detectable amount of virus, okay, for 48 weeks after stopping the treatment. That's called cure. That means cure, okay. So the undetectable limit of quantification of the virus is less than 25 IU per ml of blood. So with this therapy, treatment is very expensive, $25,000 per year, which causes severe side effects such as anemia, flu-like symptoms. This is caused by the interferon. Okay, so what is an ideal drug? So ideal drug should be targeting a viral replication. That's a direct acting antiviral, because you require a combination therapy. Okay, with a 100% cure rate, once a pill, and should work across all genotypes. So as you know, many of you know that combination therapy is essential to treat viruses, because viruses develop the resistance to a single agent. Okay, so, and the ideal drug, other one, should be inexpensive and affordable to worldwide patients, because there are 170 million people are affected worldwide. I mean, I just listed here, just in general, how you approach, how do you design antiviral agents? Of course, first thing that you should know is what is a viral genome. Okay, that is done by a biologist. Okay, understand the replication system, pathogenesis of the disease. Okay, so the most easiest thing is repurposing of the drugs, which means that test existing antiviral drugs. Okay, like for example, COVID-19. So they're testing all sort of antiviral drugs, such as influenza A drug, which is approved, and other one is remdesivir, which was discovered for Ebola virus. Okay, so these are antiviral agents. These are nucleoside inhibitors. And develop a vaccine, which is not an easy thing. So this is the fastest way if those drugs doesn't work. So it takes 12 to 18 months. Okay, but you can only develop vaccine if the mutation rate of the virus is low. Okay, so if the mutation rate is very high, like hepatitis, you can't develop a vaccine. So next thing is understand the viral replication, okay, and then identify or target each stage of the life cycle. So that's called direct acting antiviral. So this is a really long process. This is called drug discovery. So finding a small molecule which takes anywhere between 10 to 15 years if you are lucky. So to do this discovery, we really need a robust enzymatic and cell culture assays. Okay, in the absence of these robust assays, one cannot optimize needs, and it's very difficult. Okay, I just listed here based on the virus. It could be fusion inhibitor, if possible, reverse transcriptase inhibitor, in case of like other virus, like we had HIV. Protease inhibitors, most of the virus have this. Polymerase inhibitor, most of the virus have this. And then capsid inhibitor, viral assembly. And the last one is if you don't know the mechanism, the way the virus replicates, so one can do phenotypic screening, that means cell-based screening, to find any novel compound with unknown mechanism. Okay. So to do that, you can screen library of compounds against either biochemical or cell culture assay, okay? Or you can do virtual screening, okay, from the collection or literature compound. If you have X-ray structure information, that will definitely help, okay? So to do lead heat and lead optimization, we really need a biologist, chemist, and pharmacologist. So this is a continuous process on during optimization. That's the SCV, this is SCV replication and the way it works. So SCV virus has a 9.6 kilobyte base pairs, which is a positive single strand RNA. So remember that this was identified in 1999. Before that, it used to be called non-A, non-B. So this is hepatitis C. So it belongs to flavividae family. So the virus fused to the, in this case, human hepatocyte, undergoes endocytosis and release its genome. Okay, this is a positive strand RNA. So that means a positive strand RNA recognized by the ribosome, undergo translation, make the polyprotein. This polyprotein is cleaved by the viral protease as well as human protease into, in this case, 10 subunits, such as basically two types. One is called structural proteins and then non-structural proteins. Okay, once these are cleaved, these structural proteins form a replication cycle, replication complex, wherein so the positive strand RNA is translated into negative, and then a negative strand DNA is copied back to positive strand RNA to make a copies of that. Once you make a copies of the virus, this is packed into viral proteins and then undergo exocytosis and infect other cells. Okay, so NS3 and NS4B, NS5A, and 5B, these are the one constitutes a replication module. Okay, so as I said, highest mutation rate of RNA, which requires a multiple drug targets. So when the company basically initiate the program, it's a full-time commitment. Okay, because you need to target each life cycle, each step of the virus life cycle. Okay, so during that time, there are only two targets that were known. RNA-dependent RNA polymerase. This is an enzyme which is essential for making copies of the RNA. NS3 and 4S, this is a serine protease to cleave those polyproteins. So the first step is, first step it comes to biologists. Okay, one has to develop the assays. For this example, biochemical assay. So we just isolate a protein and then test compounds against that, see if there's any replication of in vitro. So the NS4A. So the next thing is a cell culture assays. I will talk about this. So because hepatitis C is a very difficult disease, because you cannot infect this hepatitis C virus into other cells. So that's why the Morgenschlager, who developed the subgenomic replicon. So I will explain you what is subgenomic. So that means it's not a full length of RNA, okay, to drive a SAR. So remember, after 10 years after the HC was identified, he developed the replicon cell line to do SAR. So the thymidine uptake assay in human hepatocyte cells, which is to measure the toxicity of the compounds. So when I talk therapeutic index is a ratio of CC50 and EC50. So as I mentioned in vivo, so when you're doing a lead optimization program, one needs to know what animal models we can try before we go into humans. So this is we need a preclinical model. So there are no preclinical model that you can develop for hepatitis C. The only animal models that you can infect is chimpanzees. So it's using chimpanzees as during a lead optimization is impractical. Okay, so now everyone is relying on the Morgenschlager replicon assay. This is the one I'm going to say many times, the replicon. So this is the cell-based assay to drive the SER. Okay. The question is, yes, you develop the subgenomic replicon assay. The question is, how do you, so here, the two choices, you have to do tests in chimpanzees, or you take directly, take compounds, selected compounds into humans, okay? So after doing a preclinical tox studies. So one of its kind is done by Boehringer Ingelheim in 2003. So they had an NS5A protease inhibitor. They directly took this compound from cell culture to clinical trials, just to show the proof of concept, to validate a cell culture assay. That's a Morgenschlager subgenomic. So just here, this is called subgenomic replicon. So that means you can see here, these are the structural proteins. Okay, so in the subgenomic replicon, the non-structural proteins, okay, non-structural proteins like a E, P1, P2, and NS2 were replaced with the luciferase gene and also eubneomycin. Basically, this eubneomycin will, which is resistant to gentamicin antibiotic. Okay, so once you construct this gene, okay, you transfect a human hepatocytes, undergo some replication. Some do not have the whole genome. So what you do is, this is a gentamicin selection. So gentamicin select compound that do not have a full genome sequence, such as no transfection, no replication. So then you clone the cell and expansion, you have replicon cells here. So in human hepatocytes. So what you do assay, you incubate the compound with and without the presence of replicons. Okay, the compound that inhibit effectively will reduce luciferase activity. So that's where we measure the luciferase activity for replicon assay. So this is 2003 because I was working, I started working on the NS5A polymerase inhibitor since 2000, okay? So this is a macrocyclic compound, which is a protease inhibitor, okay, which is very potent and which is a reversible inhibitor, whose KI for genotype, again, I mentioned genotype 1, this is the US and Europe or infected with the genotype 1. So this is 1A and 1B. So these are the two subtypes, 1A, 1B. You're going to hear and more about 1A and 1B during the talk. So 1A is the most hardest to treat the disease, okay? So this compound showed activity, which is 0.3 nanomolar, 0.6 nanomolar, okay? Selective against other proteases, serine and cysteine proteases. IC50 is greater than 30 micromolar with a great therapeutic index. So basically, since there are no animal models, the best thing would be, just to do, in Canada, just to do dose humans, after doing a preclinical talks. So they dose this compound 200 milligram twice daily for 2 days. They have seen a greater than 2 log reduction of RNA viral load. Okay, this is an important milestone in the CV field because everybody is impressed and also believed subgenomic replica. Now you can establish a benchmark for this target. So now you can use what was the activity in subgenomic replication. Let's say this compound, how it is translated into humans. Okay, so and remember that there's always a reason why we made a macrocyclic compound. Why they made a macrocyclic compound? Because this, if you see, this is a peptide here. Here is like a derivative of glycine, and you have protein, and here. So the peptide is generally not stable in the gut. So in order to optimize a compound for oral, so what we do in chemistry to make a macrocyclic compounds. Now it's easy making a macrocyclic. You can say, oh, you can make a macrocyclic compound, but it comes with a lot of challenges. Making a macrocyclic compound is very extremely difficult synthetically. But this is the first compound that they have tested proof of concept. So because it's working, because this is not a peptide. So after my postdoc, I joined in a company called Shard Biochem. So that's where I started working. And during this time, I was talking to Kumar all the time, how we're optimizing compounds, starting from a lead. This is called the thiophene lead. Okay. So which is showed 14 micromolar for NS5A polymerase. And it's very selective for DNA polymerase. It's very important. You don't want to block the DNA polymerases. So SC50 is greater than 50. Compound is not that potent, 40 micromolar. We have a long way to go and optimize the compound, okay? So as you can see here, what has been modified here, the sulfonamide was modified to amide, and then instead of, and then go to tertiary amide, basically here. This compound is equipotent against genotype 1A and 1B. This is very important. One has to have a balancing activity for genotype 1A and 1B, because if you want to treat all genotype subtype patients, you don't want to have a big difference in activity because it's difficult to adjust the dose, clinical dose. So we had a clinical candidate after 2 years, 3 years, okay? At this stage, Shire decided to close the research. Shire was a generic company. So then there was a spun-off company called Virachem. Okay, so basically Virachem has got all the rights of this compound and then started a biotech company. It was a successful biotech company where they identified a most potent compound and replicon, which is 9 micromolar. This compound EC50 in the presence of human serum, which is 40 nanomolar. We have great therapeutic index 3900. Oral bioavailability is very good, 40% less in PEG. Okay, so this is a successful story for Virachem. So it's a biotech company. So during so Vertex, on the other hand, the US company, so they had a protease, I will show you in a moment. They had a protease inhibitor. So they're looking for a polymerase inhibitor. So they're trying. So they're looking, see if any company can have a collaboration. So basically that's why they purchased Virachem. I will show you in my next slide why they purchased for $400 million in 2009. US dollars. So that's, I call them that is a great successful story, even though we lost a job, but that's successful. So these, after Vertex bought Virachem, the 2 more compounds have been developed. So you can see next slide. So this is just give an idea how it will come. So EC50 is a 9 nanomolar here. So VX222, so they dose patients 750 milligram twice daily, okay? For 3 days, you can see in all 5 patients, you have a greater than 3 log reduction in viral load, okay? So that's the reason why Vertex paid $400 million, because it works so well that this was the time that was the best compound, because a lot of compounds from big pharma, other companies, they failed because due to a toxicity, liver toxicity, because we are this is a liver disease. So liver is already compromised, okay? So when they tried for patients, so they failed because it becomes so toxic. But this compound did not go further. 222 for different reason, not because of compound is a problem. So compound is good. So recently in 2011, okay, so FDA approved NS5A polymerase inhibitor. So this is a nucleoside inhibitor. It's called a monophosphate nucleotide prodrug. It's a prodrug, okay? So they paid $11 billion to Pharmacet, okay? Gilead paid $11 billion. This is one of its kind, the big transaction for just for one compound, okay? Everybody in the industry said it's a bad decision to pay $11 billion, but everybody turned out to be, most of them turned out to be wrong because they made 20 billion in a year. So in a combination with other drug. So this is another nucleoside has been approved, Dasabavir. When Vertex bought so there are 2 compounds, right? One is this is a nucleoside inhibitor, other one is a non-nucleoside inhibitor. So important message here, in general, nucleoside inhibitors have a higher barrier to cross resistance, which means it don't develop the resistance so fast because this is not an active site inhibitor. So this is like a chain terminator, you know. So that's why the beauty of the nucleosides, when it works so good. If it doesn't, it causes a lot of tox. That's the beauty of the nucleoside. So that's why you see remdesivir is another nucleoside. Seems like working for COVID patients, people who are, you know, in fact, if you can treat early rather than late. So it's only 2 drugs available for this class, NS5B. So that's the first class. The second class is NS3A protease inhibitors. Okay, the Vertex. Vertex is this drug name is this is a scientific name, Telaprevir, and the name ends with the Previr. So Vertex has launched this drug in combination with the interferon. Okay, so and at the same time, Merck also launched the drug Bosiprevir. It's called so. These both drugs have shown SVR, viral SVR, the response is greater than 79% for genotype 1 patient. Still, this is a better than 50%. So I think Vertex made $1 billion in a year. So you see these Telaprevir, Bosiprevir, these are simple peptides, okay? These are irreversible covalent inhibitor. As you can see that serine protease attacks here, the keto here, and the keto there, okay? So that's why, first of all, these compounds use a high dose. The second thing, these are covalent inhibitors. So you don't want to have a covalent inhibitor. So you want to have a reversible inhibitor. So one of its kind is Cimeprevir. As I've shown you, the first compound that showed a proof of concept is a macrocyclic compound. This is basically, you can say, this is designed based on the BILN 2061. Cimeprevir is approved later after 2011 in combination with interferon. So the recently other protease inhibitor you can see here, Glecaprevir, Grazoprevir, Paritaprevir, Voxeloprevir. You know, these are the name always end with the pre-VR. Okay, so these are also macrocyclic compounds. These are also reversible inhibitors. You can see these are a highly complex molecule. If you ask any organic chemist, they say these are very extremely difficult. It's difficult to produce good amounts, you know, if you want to market these drugs. But amazingly, they have done a wonderful job by discovering these compounds. But you see these Glecaprevir, Grazoprevir, Voxeloprevir, they are clones of each other. So you can say fast to follow up. So all these three come from different companies, okay? They are very close structure. They all have a cyclopropyl difluor here. So this compound is a combination of this and a combination of the Grazoprevir. So you can see here, cyclopropyl difluor is coming from there, and this side is cyclopropyl, and the only thing that they introduce is another methyl. So each compound discovery has its own story. I have no idea what it is, okay? But just to show you how difficult these structures, how complex they are, okay? One, can you guess how many isomers you can generate for each one of them? You can see here. In case of Glecaprevir, you have 1 out of 128 isomers. So the chemists have to fix each stereochemistry during the optimization, okay, during the synthesis. Okay, you have to have absolutely optically pure compounds. In case of Grazoprevir is 1 out of 128, and this you see this is the monster is 1 out of 256 isomers. So the way you calculate the number of isomers is 2 to the power of n. N is nothing but a number of chiral centers present in the molecule. So this one has got 8 chiral centers. So oxaliplaprobate, okay, this is been approved very recently. So that's the background. So I'm going to talk about the discovery of NS5A replication complex inhibitor. This is a whole genome from 5' to 3'. That's a NS5A. As such, NS5A is a large phosphoprotein which is no apparent enzyme activity. Okay, it start to play a key role in viral replication, viral assembly, and also modulate host cell regulation. So how you confirm target engagement was confirmed by site-specific mutation. So if you mutate in NS5A 1N3H, your compounds lose activity. So this is the one you're going to hear during my presentation, 1N3H. Compounds were screened using a replicon assay. As I said, this is called phenotypic screening to identify a lead. So I'm going to tell you the story of the BMS. That's not my work, okay? So this is very, very important story, very unusual. You will, very few, always great discoveries comes as a surprise. Okay, this is immunothiazolidinone lead. It's called BMS 858. Okay, so only one chemotype was identified by phenotypic screening out of 1 million compounds. Okay, this compound, this chemotype was made as a part of an opportunistic library, which means that each company, they want to have a collection of compounds, so they make a novel scaffold. So that's where this compound came from, because this scaffold is easy to make basically from the readily available material. So immunothiazolidinone BMS 858 shown the activity against genotype 1b is about 1 micromolar. Okay, compound shows a great therapeutic index CC50 is greater than 50 micromolar. So this compound is not active against the existing targets NS5B polymerase and NS3A protease. So we really need to improve the activity in order to confirm the mechanism of action. So basically, typically what we do once we identify heat, okay, so we just make a quick modification just to see whether there is a trend in SER. So that's here. This molecule has a 3-point of diversity. On this side is an amino acid. This is a fluoroimine moiety here. Another one is a furon. Okay, I think most of you have learned SER structure activity relationship. I just show you here when you modify when you change the configuration from S to R, or this. So you see the activity is jumped almost 100 times. Okay, you lose activity by 104. Okay, if you remove the chiral center, the compound you lose 10 times. But if you make the ring from this methyl to this nitrogen, you retain the potency. And it's just true for other isomers. Compound is not active. And the next step, what chemistry will do? What is the easiest thing that you can modify? You remove the carbo, or this phenyl methyl carbamate to a simple amide, because making amide is very easy. So you make amide, you see is not much change when you remove this oxygen there. So when you remove this oxygen, it becomes an amide. So that you don't change the activity that much, but you reduce the number of carbons to 1 carbon. Boom, the activity is jumped by more than 100-fold here. So the 5 nanomolar compound here. Okay, and this is the trend is, again, if it is true, you can see when you make the ring here in the same stereochemistry, you retain the potency 2 nanomolar. Similarly, this fluorophenol can be replaced with the other bunch of compounds here. You boost the potency. That's like a morpholine moiety introduced on the para position of this amine. So quinoline also improve the activity. And here another modification what we can do quickly is furan replacement with the nitrogen. You boost the activity from 0.57 to 2 nanomolar. That's a quick SCR1 will do, because you should not take a couple of chemists will be working on this and made a modification. So I'm very excited about this result. As you can see, compound 2 and 3 showed greater than 5-fold and 6-fold less active against. So as I mentioned here, Y93H, this is a mutation in the NS5A protein in domain 1. So if there's no mutation, the compound is active. But if you test against this mutation, you lose the potency, which means that compound is basically going onto the NS5A protein. So, and also they have also produced other mutation within the protein, which is the L31V and Q54L. I mean, you don't have to remember this, just for for example, I'm showing here. So the compound 3 is 350-fold less active. Okay, so which means that compound is engaging in the NS5A protein. Okay, now the next is, are these mutants can be suppressed by other class of drugs? Okay, if it doesn't, then it's not good. So you can see here, this mutations or remain sensitive. That means these mutations are suppressed by NS3 protease inhibitors. That means that you can use these drugs in combination with the NS3 protease inhibitors. That's complementary. Basically, the mutation in one class will suppress by the other class. That's what you need in antiviral drugs. So this mutation study further confirms that this screening lead inhibit the viral replication via novel mechanism. It's called HCV NS5A. Still, it's very difficult to understand how it's really doing. They don't have a full X-ray structure of the NS5A protein, but nevertheless, the compound is active against NS5A replication complex. So, what is next? Well, compound 3. This is before I go, I'll show you here. Okay. So it's aminothiazolidinone. So as Dr. Reddy mentioned in his first day of the talk, rule of 5. Okay. So that means that molecular weight more than 500, log P more than 5 will have a issue for the absorption. Okay. You can't develop oral drug. Okay. That's the message. And also, this scaffold has another problem. This has an epimerizable center at C5 here. Okay, that's what you don't want. So the compound 3 undergo slow oxidation upon standing for several days in DMSO and giving to thiohydranone impurity. Okay, undergo oxidation here, and along with the other minor impurities such as thiourea and keto acid, you don't want to have that. So another thing is compound 3 is not only oxidizes in the air, but also unstable in replicon medium. That's a cell-based assay, replicon medium. Okay. So interesting observation is that replicon activity of the 3 is preserved regardless of the extent of degradation. That means compound even is not pure, still showing activity on the replicon. So that's puzzling. So what they've done is HPLC analysis of material extractor from the replicon media revealed there's no additional peaks by UV. So there's something else. The conclusion is, so antiviral activity is coming from the minor impurity mixture. So typically when we screen the compounds, usually we have multiple hits, okay? If we get this kind of information, we just put the lid and then move on to the next hit. But in this case, they have identified only one chemotype. Moreover, the compound is going into NS5A. So there's a more curiosity, what is this impurity? So, because if the activity is coming from the impurity, you can imagine activity itself is 1 nanomolar. If it's coming from the very minor impurity, you can imagine the potency of this compound. So what they have done is they took the compound C, okay? So, and they incubate in the presence of replicon medium. It's on a preparative scale. So they have identified 3 additional peaks. So 2 of them are structurally related, okay? We call them peak 4 and peak 6. Peak 4 is 43 nanomolar and peak 6 is 600 picomolar. So they have identified, once they are isolated, they identified the mass of those peaks. So it's interestingly, peak 6 converted into peak 4 upon heating in acetonitrile, okay? Which shows that we're not sure the peak 4, peak 6 are ultra-isomers or geometric isomers. So based on the mass spec, based on the observation that compound 4, so this is the compound giving an activity, not the monomer, okay? So what is the problem with this? So after discovering dimeric compounds, such a very potent compound, it completely changed the direction of the program, basically. So what is the problem with this compound? The compound is 1139 molecular weight. So comes with the structural complexity. You have 2 chiral centers, 2 coordinate centers, okay? If you want to take a lead 1139 as a lead, if you optimize, you end up with a 2000 molecular weight, or you want to cut down some weight. So that's in a way, you have no choice to continue. So that's courage from the management or the scientists. So what the medicinal chemistry do? Simplify things, okay? You have a compound 9 here, okay? So you can see here, you know that based on the preliminary SCR, we really need a amino acid portion here, okay? Amino acid residue cap, and you may not need this portion. So the best thing would be just the way you weigh the molecule, you just cut down this and giving back you that still bean. The still bean 5A, it gave genotype 1B activity is 86 nanomolar, okay, which is incredible, 86 picomolar compound. And if you reduce a double bond, you lose the potency. And so it's give you nanomolar activity. So as I mentioned, so compound 5, again, whatever you do, again, you test against Y93H mutant. Compound 5A is lost activity by 10,004, which further confirmed that 5A is still going into NS5A pocket. What is the problem with this compound? Now we have another problem, because this compound showed replicon activity against genotype 1A is greater than 10 micromolar. You can see it's going from 86.1 nanomolar to greater than micromolar. So you cannot, so now you need to fix the genotype 1A activity, okay? So because genotype 1A is a major subtype in the US, so if you want to treat those patients, one must have a genotype 1A activity. And also not only in the US, there is significant prevalence in South America, Europe, and Australia. So activity against genotype 1A is a major hurdle to overcome. So what one should have a balanced activity against 1A and 1B. Okay, this should be crucial for the program. If you don't, this program is canned. So what is the problem with this? Again, 5A is a new lead. This compound has double bond. Double bond has a propensity to undergo cis trans isomerization. So one do not want to have a double bond in the molecule. Okay, so especially for this antiviral drugs, because you treat the patients very long. So now you take, basically you take compound 5A. So you know that we know based on the preliminary CR, the activity is very sensitive here. By modifying this amide, you can get a better activities. So therefore, there's skin number of compounds, and then they make a different amide. They turn out to be the isoquinoline carboxamide showed a balanced activity. This is their bench carbon. So excited about this activity, 19 nanomolar and 7. So there's only about 2.5-fold difference in activity between 1A and 1B. That's what you want. So they modified, you see what required a pharmacophore. You basically, you just cut the molecule here. So you're giving you a phenyl there, and you have an N there, and then you put the methoxy here, you move the methoxy there. So you come up with a different cap residue coming from the phenyl glycine here, compound 7. And because double bond is a liability, you want to change a double bond to triple bonds because there's no issue of isomerization. It's just a single compound structure. So going from 7, okay, now we got now the structure is simplified. Okay, we still have a problem to solve with genotype 1A activity in compound 7. Okay. After the optimization, it's simple. This is the benzimidazole. This is called a benzimidazole moiety here, and here called imidazole moiety. Okay, usually benzimidazole compounds usually hydrophobic. It's difficult to formulate, so one needs to have imidazoles in order to formulate. So going from here, if you count the length from this nitrogen to this nitrogen, and here this nitrogen almost maybe similar or a little bit lengthy, because what you have done is you just cut down this phenyl here, cut down this phenyl here, and put the 2 phenyl in between. So that's where compound 8 was discovered here. Very impressive at 28 picomolar and 7 picomolar for 1A, 1B. What is the problem? This compound is not absorbed as expected because the molecule is basically molecular weight of this compound is very high, which is beyond the Lipinski rule, 807 molecular weight. Okay, so what the chemist will do, where else you can, you can't remove this, you cannot remove this, you cannot remove this. What else you do? The only thing that you have room left is only here, the phenyl modification there, because the phenyl contributes to the high molecular weight. So you take the phenyl, you modify to valine. Now a new issue comes to picture. So GT1A activity is now it's a micromolar. Micromolar in 1A, 1B is 1.22 nanomolar. So as Dr. Reddy pointed out, that every problem that you face, you need to fix by making a new molecule. So this is a reiteration, continuous process. Each problem is solved as you go on, basically. Now the key is for this program is you need to have genotype 1A, 1B activity should be almost equal or maybe a few fold higher. So, but again, what chemists do, we make the isomers of this valine. So you make, going from the, this is our molecule, okay, going from R to S. Now you bring back the genotype 1A activity similar to compound 8. So now it's a 50 picomolar against 1A and 9 picomolar against 1B. So this is the miracle compound, okay. As you can see here, there are 4 chiral centers. I divided by 2 is because the C2 symmetry. So give you 8 possible isomers. This compound was dosed in rat, which showed oral bioavailability is 50% in rat, and dog is 100%, monkey 38%. So I just want to take a moment. I want to say that. So they identify a good compound. So we know that this is a liver disease because the hepatitis C replication primarily in the liver. So you want to have a higher level of drugs in the liver. Okay, so they need to understand what is the liver to plasma ratio. Okay, when this compound was dosed in rat, 5 milligram per kilogram. Okay, so at the 24 hours, okay, so you have 103 nanomolar is there, which is 5-fold higher than the plasma. Okay, so if you want to develop this compound as a pan genotype, you want to have enough drug level should be higher than EC90 of EC90, yes, EC90 of the all genotypes. So this is the EC90 of the least sensitive genotype 1A after protein adjusting. The activity is 383, which is much significantly higher. The drug levels are significantly higher than the EC90 383 picomolar. So this is very impressive. The next question is, this is a replicon, right? So this is the NS5A class. We don't know whether does it work in the human. So once you've done the clinical trials, once you've done the preclinical talks, so you want to put this compound directly into human and see the efficacy of the viral load. Okay, just before going into that, the activity of this compound shown here, the compound shown against all genotype 1, 2, 2A, 3, genotype 4, 5, 6. You see all of them are, they're all picomolar compounds. The most least sensitive is the genotype 3A, which is 146. These are Y93H mutations, so it doesn't matter because you're going to use in combination with the other drugs that are sensitive to this mutation. So as I mentioned, if you want to cure HCV patients, so you need to have one should have a pan genotype activity. So that's what this compound has. That is an incredible discovery. So this name is called daclinza. This is a HCl salt, as I mentioned here, because everywhere the molecule is hydrophobic. So you have a 2 imidazole in here, so you make a 2 HCl salt. Application is 1A. The question is, does it work in the clinic? Okay, so that's the result here. So this compound, upon single dosing 100 milligram of this dichloride salt, okay, within 24 hours, within a day, the viral load dropped by 3.5 log, which they never seen with any other drug. Okay, so oral bioavailability. So this is a single dose, and in 24 hours, that's the incredible efficiency of this compound. So oral bioavailability is very good, 67%. As Dr. Reddy mentioned, this compound shouldn't be orally bioavailable because this one, the molecular weight is greater than 700. You have more than hydrogen bond acceptors. So, but this compound bioavailability is 67%. Okay, protein binding hardly matters. 90 still you have 1% is available because the compound is so potent, which is picomolar. So 1% free fraction is more than enough, okay, to see the efficacy. So, because this proof of this in the clinic was presented in 2010, okay. So when this patent was published in 2008, when we were working on HCV on different targets, we were working on NS5A as well, okay. When we saw this patent, everybody just basically stunned. They said, these molecules are very ugly molecules, you will have a lot of problems, this is just a patent. So nevertheless, we went ahead. And so if you want to screen compounds, again, it's very difficult to find like this structure because in your database, you do not have this type of compounds, So what we decide as a chemist, how, again, this one on study, how do you design, right? Lead comes from different sources. As Dr. already mentioned, on one of the sources, natural product, take a natural product lead, or by screening or by designing, okay, of the existing compound. So that's where we started working on. I will just show you what we have done towards NS5A. So we have inspired by this pattern. So what we did is that this is again, this is it's very close. This is basically imidazole. So we made a benzimidazole because we didn't know that they have made a benzimidazole because there was no patent published. So we just made the benzimidazole. So it's dimer, okay? So this is dimer. So if you connect the benzimidazole together, so basically we still have activity 26 nanomolar. You know, when you start a project like 26 nanomolar, it's pretty impressive, but this compound does not, is not good activity in genotype 1A because one must have a genotype 1A activity. And CC50 is greater than 20. If we increase the length, put the triple bond, you start getting the genotype 1A activity. If you have a floppy molecule, if you reduce, again, it goes bad. You increase the length to the two triple bond, okay? So you start getting back the genotype 1A activity. Now we put the phenyl ring there, para, boom. So we got a balance. So now we got a 500 picomolar compound against genotype 1A. So for us, this is the benchmark compound. This is the lead. If you have a meta link here, you lose activity. So basically, now we have identified a compound that has a balanced activity. Okay. So next is to improve the 1A activity. So I'm not going into full SAR because at this stage I just want to show you that what we did. So we identified this compound. This is a bis benzodol, the 2-alkyne, which is 18,000 picomolar. Okay. Now we identified this is a hybrid molecule of the benzimidazole here, and then imidazole there. Okay. So this compound is EC50 is a 13 picomolar against 1B, and against 1A is 140 picomolar. Still is a very good compound, but there's always a danger because this compound is almost like, looks like a BMS compound. There's always danger. I'm sure if you thought about this compound, I'm sure chemists think the same way. They should have thought about that compound too. But what we did is we put the methyl group on the proline here. Now we generate another extra chiral center there. Okay. Usually we want to avoid that, but now we have no choice because we need to have a novel entity, patentable compound. If you cannot patent, so the program is dead, literally. So you will not see this kind of a jump in activity usually. If you put the methyl there, you have 1,000-fold improvement for genotype 1A. So going from 18,000 picomolar to 18 pico. Now we have a same activity against both 1A and 1B after putting the 2-methyl group here. And this one is still translated here. Now on the hybrid compound, you put the methyl there. Now we have identified a single digit picomolar compound, and we have an imidazole compound, which you can make a salt, and CC50 is greater than 20 micron. You have a therapeutic index, you can calculate yourself. So it's tens of thousands, okay? So this is the work that we have done in June 2010. The patent was published in 2008, and we have 2010 this compound, okay? So within 1.5 years, we have done the first follow-up and identify a compound. But what is the next? For different, we have different corporate strategy because Gilead come up with the nucleoside lipid. No, actually, no, that's not true. What happened is when we had a compound this, within a week of time, there was a patent published that covers a methyl proline generically, but they have not exemplified, not in a single example, but it's a risky, you don't want to put your money and develop this compound, and after that, we will have an issue with that. So that's why we did not go further. So I stopped at this one, but you can see what we thought, okay, that's 2010. Everybody, okay, just show you the activity for this compound. You can see the compound there's no CYP inhibition, which is good for a combination drug because it does not cause any drug-drug interaction. There's no hERG inhibition greater than 30. Compound is still, we have a plasma protein binding 1.4%. There's no permeability issue, CACO2 MDR efflux ratio is very good. And when this compound was dosed at 3 milligram per kilogram and PEG, so you have a half-life is 3.5 hours and bioavailability is very decent at 26%. So that's the end of the story for this project. But chemists think differently. So this is where Dr. Reddy said one need to have a total synthesis training. Okay, if you don't have a good training in organic synthesis, now we can teach medicinal chemistry, but we cannot teach organic chemistry in the industry. Okay, so the best thing, you need to have a good training who is doing a total synthesis like Dr. Reddy. You saw the presentation. So this is the art of chemistry. So that's a BMS, the molecular weight is 768. This is called ledepisivir from Gilead. You can see here they have a 6 chiral center. This is 1 out of 64 compound. See what they have done is that you have a basic pharmacophore. You have this is a methoxycarbonyl here, valine, and they modify the proline here. They modify it here. So this is a lengthy synthesis, but one has to have a good training to make all these compounds here. Velpatasvir is also from Gilead. You see, this is like a heterodimer. You have a 6 chiral centers, 1, 2, 3, 4, 5, 6. Okay, so again, molecular weight is very, very high, 913. And this is from Merck, elbasovir. Okay, so we have a 5 chiral center, molecular weight is 900. Abitavir. So always these NS5A drugs end with the SVIR, severe. Okay, tasavir, wasavir, whatever. Okay, so this is a scientific name to identify the class of the drug. The molecular weight of this abitavir is 900 plus. And this is the recently approved pibrentasvir from Abbott. Look at the molecular weight here. If you ask anyone, if you ask any medicinal chemist, said without knowing, oh, this is a crappy molecule. I don't think this compound is orally bioavailable because it breaks all the rule in terms of the molecular weight and also in terms of the hydrogen bond acceptor, and so that's why. And there is a benzimidazole. These compounds. I'm sure that a pharmacologist, I'm sure, might have done an excellent job to find a formulation for this compound, because you can't make the salt for this compound. Okay, so there's no basic nitrogen that you can make a salt, whereas even for this, but whereas this compound, you have a basic nitrogen which is called imidazole. You can make a salt. Same thing here, you can make a salt. Here you can make a salt, but not for this. I have no idea. I have not checked the formulation of this compound, but I think it's for the student. It's a homework for the student to check formulation of these compounds, how they improve the oral bioavailability of these compounds. So this is how HCV treatment is evolved. So there are two types. One is interferon combination, and was the interferon regimen combination. So this is the genome. First genome was discovered in 1989, and later it was approved in 2000 with the PEG and in combination with the ribavirin. So this is the first proof of concept. 1999 Borderslogger replicon cell culture was developed after 10 years. See how difficult it is to find a cell culture. This is an incredible scientific achievement, 1999, then followed by the first proof of concept demonstrated by Boehringer company. And the Vertex, it's our former company, Vertex and Merck have basically marketed two drugs, one drug each in the same year, almost not much different. So because they were approved in combination with PEG interferon. So this is a protease inhibitor. That's where the dynamic change for Vertex. When Vertex, so this is the Sovaldi. Sovaldi is a nucleotide, basically. It's a prodrug, nucleoside prodrug, which is approved in 2003. So this has got a better efficacy, 95% cure rate for genotype 1 patient, followed by J&J, Olicio, they put the macrocyclic compound. So from here, everything changed. So once they had NS5A inhibitor, everything changed. That's why I said NS5A inhibitor is a game changer because you don't require interferon, you don't require a ribavirin. Okay, so Harvoni is from Gilead, which is NS5A inhibitor, and NS5B is a nucleoside inhibitor. So Gilead is the one who made enormous amount of money within a year. Like they made like about $15–20 billion, you know, because Sovaldi is so good, works well with the ribavirin, and also it works very well with the Harvoni. So there's not much drug-drug interaction. So. And then Abbott I come up with the 4 compounds. It's very complicated. Unlike Gilead is very simple. You take one pill, that's it. So, in 2015, even the BMS is the one who showed NS5A works in the clinic. They're a little bit behind. So in 2015, they marketed because what happened is the BMS had a collaboration with the pharmacist. So in fact, they were in advance, like, you know, in Japan. So they're doing clinical trials with NS5A, with the Sovaldi. When Gilead bought Pharmacet, now that Sovaldi goes to Gilead, NS5A. That's where the, you know, so the BMS has to look for other combination drug. So the Epclusa japatia, so another 2 drugs. Basically, this is Merck. Again, this is from Gilead, Epclusa. So each milestone they have a different cure, right? So as you can see here, without NS5A, you can't treat HCV patient. So that's very important. So very important. So Gilead put another drug. So basically, Gilead put 1, 2, 3, 4 drugs in span of 3. So Gilead is very, very aggressive. Basically, you know, the NS5A patent was published in 2008. In 6 years, they had an NS5A compound. So this is incredibly fast. So 2017, Wasabi, it is an NS5A inhibitor, NS5B nucleoside. Another one is a protease inhibitor. Okay, so this is called Maviret. This is from Abbott, which has only 2 drugs, NS5A and the protease. So if you see here, that's from the Abbott protease. Okay, and yeah, that's about protease. And for Gilead is Gilead NS5 drug is valpapatinib. So that's the evolution of how HCV treatment happened. And you can see here, like Imsivec, Victrolis, Policio, Vikiera Pack, Daclinza, Technivi, all these drugs have been discontinued because there are other better drugs approved, such as like Gilead compound, Epclusa, Wasabi. So because there's no market for this, you know. So this is a final summary. So Wasabi is from Gilead, which has a nucleoside, valpapatinib and oxaliplatin. Okay, this is a pan genotype, which is genotype 1 to 6. You can treat. So approved for adults without cirrhosis or with the compensated cirrhosis. So this is very, very difficult. So your liver is already compromised. Who are treated previously with NS5A inhibitor, okay, or genotype 1A or 3. So genotype 3 is present in India. Who treated previously with the sofosbuvir without NS5A. Okay, treatment period is very 12 weeks. So PEG interferon is a 48-week. In CIVIC, they reduced to 24-week. Now you're reduced to 12-week. So it's very short, compared with the previous therapy. So it's a QD, it's a single dose. Single dose works for all genotypes. Okay. Only side effect that you see is a headache, fatigue. And the most importantly, because some people are co-infected hepatitis B, some warnings for because some patients HBV is reactivated when treated with these drugs. So you cannot use these drugs who are taking rifampin. Okay, the cure rate is again I emphasize SVR12 is sustainable virological response. That means that there's no detectable amount of RNA virus. Okay, after 12 weeks, stopping the treatment. Okay, so the overall cure rate is 96% for all genotype 1 to 6. If you just count only for genotype 1B, 2, 5, 6, which is 100% cure. That's the ideal drug, but still price is very pricey. It's a US dollar 60,400. But if you think about liver transplantation, because this is drug approved for compensated cirrhosis. Okay, so if you want to do liver transplantation, it costs you over $500,000 and above. So 60,000 is very good because this is a cure. This is not a lifetime treatment. So in 12 weeks, 12 weeks over 3 months, you are done. So basically you are cured. So that's how incredible it is. So the most recent compound is a mavorate, AbbVie compound. Again, this is also pan-genotype. Mavorate is approved for pan-genotype for children greater than 12 years. Adults without cirrhosis, with a mild cirrhosis. So the difference between these two drugs, all of them genotype 6, this one is a compensated cirrhosis. So it's a very advanced stage, and this is a mild cirrhosis. So whereas this treatment period is 8 weeks, again, this is a QD. Same side effect, you see that. Almost అయిపోయిందండి. This is my last slide. Yeah, so only patient who cannot take this one, people who have severe liver impairment and they have history of liver decompensation. And we're also taking Janavir and rifampin. So the cure rate, so this is SVR8, okay? So the cure rate is 98%. It's much cheaper, 26,400. See, HCV treatment, the cost went from 96,000 to 26,400. So it's a good news for all hepatitis C patients. This price must be much lower in India because I'm sure they have a subsidized price coming soon. I don't know if it's available in India or not. My take-home message is, get tested. Treatment is available. Don't wait, because if you wait, you're too late. So that's what the message. I think with this one. Finally, I just give you acknowledgement again. These are the leaders. It is a great team effort. This is drug discovery is not a single person effort. This is a whole teamwork, and these are the two companies that I work. I thank again for Vishnu College of Pharmacy and then Dr. Kumar and the organizing committee. And again, I thank you all audience for listening patiently. I try to answer all medicinal chemistry questions, whatever I can. So if you have any questions, you're free to ask. If you want to write to me, I have an email listed in my first slide, so you can also send me by email. So with this one, I finish my presentation.
Thank you very much, sir. So it is very informative and also very relevant to the theme, sir. And all the case studies will be, I think it will be inspiring for the chemistry people also, chemistry faculty in our college also. So stepwise process in drug discovery in all the case studies are really useful to all the faculty. So now we'll take some questions, sir. So in the video, so if in Zoom link anybody wants to ask some questions, the Q&A session is open.
Should I give a stop sharing or?
It can be there. It can be there, sir. Just they'll be asking questions. Slide can
Sure.
be. So there is a question in YouTube streaming, sir. So Sudha wants to ask. She has been reading in articles like newer drugs, interferons, etc. They are pegylated, sir. So what is the importance of pegylation? She's asking, sir.
I think I think they used for to increase the half-life of the interferon. And also solubility, you know. The pegylated compounds usually tend to have a longer half-life.
Good morning, sir. This is Sujit Kumar.
Hi.
So I have one query. When I see the antivirals, especially all the drugs which are being used or which are being in the clinical studies, why they are near to 1000 gram per moles or more than that or in daltons?
Could you please repeat again? Why?
Yeah, when I come to antivirals, the medicines which are used or which are being in discovery stage, clinical stage, why all the structures, molecular weight is touching near to 1000 or more than that grams per moles or in daltons, and they're more complex. That's what I want to know.
Well, it's because in case of NS5A, so this is like NS5A is like a dimeric structure. So it is a large protein. So if you want to have a potency, so you need to have molecule should be bigger, larger. So we don't have any molecule that have both active against 1A and 1B very potent. So the way this molecule acts, we don't know how it works, but still in the preliminary stage. But I think they have a large pocket size. That's one thing. Whereas the protease is like a tripeptide. Why they are bigger? Because first of all, the molecule can after all the interactions to increase the potency. The macrocycles have been made basically to increase the oral bioavailability, because in the gut, the peptides is cleaved by peptidases. So that's why you end up getting a big, large molecular weight. I don't know the full detail of each of them because I have not worked on those protease inhibitors. I work on the NS5A and the polymerase inhibitor. It's something to do with, because you need a minimum like a tripeptide to go into active site. And then other one is to optimize our properties. Yeah, I don't know if I answered you correct, but that's where it is. Not all of them. In general, protease compounds are always bigger in general. And the NS5A is an exception. This is not a protease. It's probably this is a protein. You can say protein-protein interaction basically. So you need a higher, bigger molecule weight.
Yeah, thank you, sir.
Yeah, welcome.
Sir, good morning, sir.
Yeah.
Sir, good morning, sir.
Good morning.
Sir, I am K. Raju, sir, working as Assistant Professor in Sri Vishnu College of Pharmacy.
Okay.
First of all, thank you so much, sir, for your valuable session. I have a small doubt about that compound, antiviral compound, sir.
Yeah.
So, is there any spectral data available for the antiviral compound, sir?
Spectral data
available for that compound, sir? NS5 compound.
Well, I don't have actually in my hand, but I think you should be able to find out if you dig through the literature. You know, they are like in case of example, like these one are relatively simple because it's a symmetrical compound. Yeah, this should be simpler because you only have the molecule spectra, you can see them. Whereas compounds like this is also C2 symmetry.
Yes, sir.
It should be okay. The most difficult thing for this protease inhibitors, it's
Yes, sir. Yes, sir.
if you person known in the art, even if you're
Yes, sir. Those are complex structures, no, sir.
thinking this is really very very complex structures. I think the best thing would be to just if drug is available, take the amount of that, or maybe because when they publish, I don't think they publish the real spectrum, because most of these compounds published in the J Medicam, things like that, maybe possible if you can dig through, probably you'll be able to find the spectrum for that.
Yes, sir.
But they're very complex. They are not easy. Making these molecules require a highly skilled organic chemist.
Yes, sir. Yes, sir.
And even manufacture them is, I don't know, because the fact that the dose is very small, so they don't have to manufacture lots of drug.
Yes, sir. Yes, sir. Okay. Okay, sir. Thank you so much.
Sir, good morning, sir. I'm Dr. Raghu Prasad speaking.
Okay.
Hello, sir. I'm Dr. Raghu Prasad speaking.
Yeah, go ahead, please.
Thank you very much for your very good lecture. Elaborately explained and precise to the topic. And I would like to know if there are any chances of these drugs which are used for influenza to be repurposed for COVID-19 treatment.
Okay, I'm not sure whether I don't think these drugs have been trying, because yeah, maybe they might have tried. Whoever discovered these drugs, I'm sure they might have tried. So yeah, I mean these are recently approved drugs. So COVID-19, if you want to manufacture this Voxeloprevir, things like that, extremely difficult. So if you find a drug like an influenza drug, it seems like it's working better. Remdesivir, I think if you find one of them is good one, nucleoside will be the way to go. Yeah.
Sir, can non-nucleoside molecules work as antiviral agents?
Yes, because they go and bind in the active site.
Okay, sir. Okay.
Because see, the difference is because the nucleosides, these are the chain terminators.
Yes, sir.
But remdesivir has been discovered for Ebola virus.
Yes.
And it's been like not that active, but it's active against other viruses. So because it go and interfere the RNA synthesis. Okay. That's the beauty of the nucleoside if it works. Okay. So, but whereas the non-nucleoside, if you don't have a active site which is similar, okay, the other virus, and it's not going to work.
Okay, sir. Okay, yeah. Thank you very much, sir.
Yeah, you're welcome. Yeah, request to the audience. I think there is a questionnaire and answers. I think I'm expecting that Dr. Kumar want to score 50%, but I want you guys to score more than 70%.
So still we have time, so if anybody wants to ask questions, please ask now.
I think it's a good. I think it's a good exercise for the formulation guys. To go and check the formulation for this one. So I have no idea what they use.
Right. That's true. Yeah.
This one, remember, this usually the oral absorption of this high molecular weight is exceptional for, let's say, antibiotics and the macrolides, right? But these are not. I have no idea whether any transporters are involved in absorbing these compounds. Yeah, but this is very unique because protease inhibitors are huge. NS5A, RCI are huge. This is HCV is very, very difficult to treat. I think, fortunately, I think great drugs are being discovered. I think it's good for the community. Yeah. I think it's, HCV is a silent killer, so you don't know that you have it, okay? So the best way is to get tested, not wait for a long time.
So Jagdish,
I'll show you some of the,
yeah, please.
yes. I think I was trying to put, coronavirus, I know people are doing this. Yeah, that's basically just give you just for information that, for coronavirus is, again, as I mentioned, this is also positive single strand RNA. So which is same class as hepatitis C. Okay. So that's a remivir, and you call them Covifur. This is marketed by hetero drugs because this is a nucleoside, right? It's going to interfere the polymerase. So that's why it seems like I'm reading the clinical trials of this, because clinical trial for this, they have tested for people who are on ventilators. Okay. But it seems like it was not effective. But if you treat early, maybe you basically
Chances are there.
recover the patients a little bit faster. So that's another one is drug is approved by Glenmark. It's called Fabiflu. So this is the polymerase inhibitor. I'm very impressed with the structure. This is the structure. That's what you want for COVID patients, because the manufacturing of this compound is very, very easy, right? So compared with the nucleoside, which is not relatively is easier than the hepatitis, but still is a good amount of work to make this compound. I don't know if you guys heard about dexamethasone.
Yes, sir.
So this is approved in UK. So what they said is it reduces the death rate by 30% who are on ventilators. So even if you say one patient on people who are on ventilators, still is good, because dexamethasone is an anti-inflammatory agent, right? So which probably reduces the inflammation of the lung. So therefore, by increases the oxygen intake. Yeah, so what I was reading, the paper. So coronavirus, okay. So the mutation rate, they said it's slower than influenza, okay. So and the hepatitis C virus mutation rate is the highest among RNAs, okay. That's why we have a hope that the several companies are doing developing a vaccine for coronavirus based on mRNA technologies, because using this is a new technology that never been manufactured, okay. So because it's easy to scale up, that's what they say. So this mRNA technology is developed by two companies. So one of them is Moderna. So Moderna has a collaboration with Pfizer. So they said that vaccines may be available as early as September. So it works. I think that's a vaccine is the way to go for this one if it works, I think. So, and also the other things people are saying about this, it's called AC2. This is the angiotensin, okay, receptors, ACE2 receptor. ACE2 receptor, it seems like involved in the
Entry of compound.
uh,
Entry of the compound, sir.
entry of the compound, basically. So they say the people who are taking beta blockers, they have a less prone for coronavirus, because they are ACE inhibitors. So they are less affected. Again, in this one, they are, I'm just stating pretty much. So there's RNA. Again, this is a single strand positive RNA polypeptides. So that's why all the drugs here, it's called drug repurposing. So lopinavir, darunavir, these are HIV drugs, right?
Yes, sir.
Yeah, so they're trying on this because they block this proteolysis. And then this one is, it's called RNA dependent RNA polymerase. That's where the remit is, where it seems to work here. So the same thing. I don't know if the NS5A inhibitor works here. You know, you have to test in the biochemical assays. First of all, we don't know whether they have biochemical assays or not. So here is the RNA synthesis, then viral assembly. So what else are people trying here? I think this is the immunosuppressants. Okay. It seems chloroquine hydroxychloroquine seems to act, but I think this seems like this compound's showing some toxicity. Okay. I think one of the interesting thing for, for the small molecules, the camostat, right, which inhibits the fusion of the spike proteins with the other subtype. Yeah, I've never seen the virus like this, it's so infectious.
Coronavirus. Yeah.
Yeah, so that's,
Anybody wants to ask any more question? Anyone from the participants of this Zoom? Any more question? So, okay, Dr. Jagdish, your presentation is awesome as usual. And I just want to add one point is you said if you talk for more than 1 hour, there will be a drop in the participants, but it is not so today. So you talk for 1 hour, 40 minutes. So whether it is the audience in this Zoom or those on the YouTube, the numbers has not decreased and it stayed consistent. And my personal observation is there's no drop here also.
I'm very glad.
So that tells you that you did a great job. And I'm really impressed with the quality, quantum, depth, and the way you explained the intricacies and the progress that you have discussed is awesome. And this is the one of the best webinar I heard in the last few months. And in fact, one of the best scientific presentation I had in the past few years. So thanks a lot. I'm sure many of these participants enjoyed it. And I know you did a very good job, and you did excellent job, not good. So I think that's the right word to say for your talk.
Thanks to Zoom technology, without the Zoom, I wouldn't have happened this.
Right, that is true. So it's helping us to connect well. Yeah. So thanks a lot. So and I also thank all the participants for actively participating in this webinar, and those on the YouTube. Again, same thing. Well, thank you all for your participation, and hope to see you tomorrow as well. Tomorrow onwards, the talks will be more concentrated on pharmacology side. So now pharmacologists will talk about drug discovery. Because what is interesting to note is all the three chemists are talked as good as pharmacologists. So it looks like the chemist has an advantage in drug discovery and development over the pharmacologists, because as pharmacologists you can't talk the chemistry, but you people are talking equally good pharmacology. Even better, I guess, in some ways, because you did the job while making the molecule to the clinic. So since there is a technical issue at the other end, so I'm doing this concluding remarks for this webinar. So thanks, Dr. Jagdish, for your wonderful talk, and all the participants, active participation on behalf of SVCP management and SVA Certificate Society. I thank all of you for active participation. Hope to see you all tomorrow again with the same N2 and participation.
I think, before I close the session, so I'd like to hear your feedback from the audience. I think any constructive feedback is welcome. Feedback.
So, yes, so I said, anyone else wants to add the feedback?
Well,
so in person also?
they want to,
you can unmute and talk.
yeah, you can summarize. You can summarize and send me the feedback. That would be better.
Yeah. So what I will do is we have the feedback forms. All the participants, those who will be watching the video in YouTube over next 24 hours or so, every one of them will give we have a feedback form. So they give the feedback, how they rate the presentation, how you conduct this organization, how is the content, and how they felt about the presenter, how they felt about the content of the presentation. So all those feedbacks are there. So that summary I will send to you.
Oh, that's great, Kumar.
So that I will share you in 2-3 days. So this video will be live for a few days on YouTube, and we expect to get the feedback within a few days. So I'll share that update.
Okay.
So I think with this, once again, thank the address. It's too late for him. Probably said it's now 2 o'clock.
Yeah, it's 1:25 a.m.
Yeah, 1:25 a.m. So we should thank him for for staying awake and giving this talk without losing any energy. So that's the indication of a good scientist. When you're talking, is forget time. And you talk continuously and so nicely. So thank you also. With this, we'll wrap up this today's session and see you all tomorrow.
Okay, thanks, Kumar. We'll see you tomorrow.